Every dataset carries assumptions, not explicit formulas or written rules, but quiet expectations about units, ranges, completeness, and meaning that shape how we interpret the values. When we talk about structural assumptions, we mean the implicit beliefs encoded in a dataset's shape and schema, assumptions about what fields exist, what they mean, how they relate, and how stable those relationships are over time. These assumptions are powerful because they make automation possible. They are dangerous because they are often invisible. In this video, we will define structural assumptions, examine common categories, show how they fail in practice, and give concrete practices to make assumptions explicit, testable, and safe to evolve. Start with a clear example. A table with a column called price carries many assumptions: that the value is numeric, that it represents a single currency, that it is expressed in a fixed unit, dollars or cents, and that it refers to the current sale price rather than a historical list price. Those assumptions determine how you aggregate, compare, or convert that column. If any assumption is wrong or changes, downstream results can be silently incorrect. Structural assumptions fall into several broad classes. First, type and unit assumptions. These are beliefs about data types, string versus number versus timestamp, and units such as meters versus feet or dollars versus cents. Confusing units or mistaking strings for numbers is a common source of bugs. Second, completeness and missingness assumptions. Datasets often assume certain fields are present, or that missing values mean a particular thing, unknown, not applicable, or intentionally omitted. Treating all missing values the same is a risky assumption. Third, cardinality and uniqueness assumptions. Examples include assuming a column is unique, or that a one-to-many relationship never has more than n children. Violations of these assumptions cause deduplication errors, aggregation mistakes, and incorrect joins. Fourth, temporal and ordering assumptions. Timestamp resolution, time zone, monotonicity, and event ordering are all structural expectations. If a system assumes monotonic timestamps but sources provide out-of-order events, causal analyses break. Fifth, distributional and independence assumptions. Statistical models and aggregations often rely on assumptions about distributions, independence between features, or stationarity over time. These assumptions are subtle and easy to violate as populations and behaviors shift. Sixth, schema stability and evolution assumptions. Many pipelines assume schemas are stable. Column names, types, or meanings do not change. In practice, producers evolve, and consumers who assume stability will fail silently or misinterpret data. Seventh, semantic assumptions. These concern meaning. What a status code denotes, whether a Boolean true means active or verified, or whether a label refers to current state or historical classification. Semantic drift is particularly insidious because syntactic checks still pass. Why do these assumptions matter? Because code, models, dashboards, and alerts are built on top of them. Assumptions compress human context into machine-readable structure, and when that compression loses crucial context, inference and automation produce confident but incorrect results. How do structural assumptions fail in the real world? They fail slowly and silently. A column that was numeric may start receiving string annotations. A new product line introduces negative prices for credits. A third-party supplier changes time units from seconds to milliseconds. In many cases, the data still loads, validations pass, and reports continue, but the meaning has shifted. They also fail at scale. Minor ambiguities that were inconsequential on small samples become critical when data volumes grow or when new consumers rely on the dataset for different purposes. So what can you do to manage structural assumptions? Here are concrete, practical steps. First, make assumptions explicit. Document types, units, allowed values, and semantics in a schema registry or data catalog. For every column, capture what a missing value means and which downstream systems depend on it. Second, encode constraints close to the source. Where possible, validate units, types, and ranges at ingestion. Use schema validation libraries, strict API contracts, or lightweight gateways that reject or tag unexpected messages. Third, version and contract your schema. Treat schemas like public APIs. Version changes, provide compatibility guarantees, and communicate deprecations. Use backward compatible, additive changes as the default path. Fourth, test assumptions automatically. Write tests that assert cardinality, uniqueness, monotonicity, and distributional expectations. Incorporate these tests into CI pipelines and data quality suites, so breaking changes are caught early. Fifth, monitor and alert on drift. Track schema changes, field-level statistics, and validation error rates. Set thresholds not only for syntactic errors, but also for semantic shifts, sudden changes in null rates, distribution skews, or new categorical values. Sixth, use defensive design patterns. Prefer explicit units in column names, use typed fields, and avoid overloading a single field with multiple meanings. When you materialize derived values, record provenance and the inputs used to compute them. Seventh, design safe migration paths. When changing assumptions, tightening a constraint, changing a unit, or renaming a field, use staged rollouts, add new fields, backfill historic values, switch producers, and then retire the old artifact. Eighth, accept human in the loop for high-risk repairs. Not every ambiguity can be resolved automatically. Quarantine anomalous records, surface them to domain experts, and record decisions so the rationale becomes data itself. Finally, consider the organizational practices that support assumption safety. A schema registry with owners, documented change processes, lightweight contractual agreements between producer and consumer teams, and post-change audits. In summary, structural assumptions are the invisible rules that make data usable, and they are also the most common source of silent failure. By naming assumptions explicitly, validating them near the source, versioning schemas, testing expectations, monitoring drift, and designing careful migrations, you convert hidden risks into manageable processes. When you treat assumptions as first-class artifacts, your data becomes more reliable, auditable, and adaptable. That is the heart of good structural design.